I just want to say that the most important first step for building any NLP application is how you can represent efficiently words into numbers, or in the language of NLP it is called vectorization. Okay, here's the process. Like, when we creating an NLP application, we translate words into numbers, and that is called vectorization. Okay, so how do we do that? Okay, for doing that we have came up with few techniques. So, people worked a lot to understand how we can convert words into numbers, and this is where some basic techniques come up. Like, the most original, the first technique that came up was one hot encoding, where uh, what you do is that you have this sentence, like this sentence, mat, cat, mat, rat, rat. These two sentences, like we have, you have to make the computer understand these two sentences. What I mean, you have to convert it into numbers. So what do you do in one hot encoding? First of all, you find out how many unique words you have in your total vocabulary, and which are the unique words. So one let me show you which are the unique words are. The first one is mat, cat, and rat. These three are okay. From these two sentences, these three sentences, these three words are these three unique words into numbers. So we can represent them as mat. Okay, how you represent mat? 100. How you can represent cat? 1010. Okay, how you can represent rat? 001. So it means that I can very easily write this first sentence like this. First sentence, like first one is 0, sorry, 100, and what is cat is 010, right? And what is mat? Again 100. So I have represented in the form of numbers to these words. Okay, and this numerical representation of these sentences, similarly I can represent this sentence as well, seconds for this sentence as well. But clearly here you can see that this method is a bit inefficient, right? So then we talked about improving it. So one more technique come up called bag of words. Okay, bag of words was a slight improvement. Here you are just seeing whether that word is there or not, but in bag of words you also see how many times that word has came. That means what you will do in bag of words, you will again write down all your unique words like mat, rat, and cat, and then you will hold each sentence and asks to each of them. Like here you can see this bag of words. You will ask to each of them, tell me brother, how many times mat came in your sentence. So here mat came twice. How many times the cat mat came the sentence for two times, and cat came for one time. And this entire sentence, in first sentence, rat has not come for a single time, so we have written it as 0. Okay, similarly in this second sentence also, so we have written here. Okay, so according to bag of words, though to improve it a little more, one more techniques, or like pf IDF. You understand this, right? You have studied all this in NLP, but the real fun came when a technique come which is called word embedding. Okay, word embedding. It was much more advanced and than these other techniques, and it was able to convert words into numbers in a very better way. Why? Because word embedding has the power to capture semantic meanings. Okay, let me explain what it means to capture semantic meanings. Okay, I mean that word embeddings convert words into numbers in such a way that the meaning of the word and the context in which it is generally used is captured. So this is the best part about embedding now. Okay, now if I give you a quick summary of how word embeddings are created, what do you do? To you take a huge training data like eh, how is it work? Let me explain you. Like you take a huge training data, like you have taken the Wikipedia. For example, suppose you have all these Wikipedia articles on the internet, you pick them all up and collect them. This is your training data, and you send this training data to a neural network. Okay, to a neural network, you have send them, and then it understands the context in which each word is used, and then it represents each word in the form of an n-dimensional vector. Each word is converted into an n-dimensional vector. This n could be 256, 512, even 64. It depends. Okay. Let's assume for a moment that we have a five-dimensional vector. Okay. I know I cannot draw five-dimensional in this way, but just take as an example. So we have captured the semantic meaning. So you can represent two words in a set of five numbers. For example, if you take that this training is complete, we can represent a word like king with the help of five numbers. Let's say zero point 0.6, zero point 0.2, zero point 0.6, zero point 0.2, and 1, 1, 0, and zero point 0.9. We can represent another word like coin with another set of five numbers. Now, the interesting thing is that since we are able to capture the semantic meaning, if two words are very similar, then their two vectors will also be very similar. And the geometric intuition behind this uh, is that obviously I cannot draw five dimensions here, uh, but I am drawing only two dimensions, like you can see here. In this five dimension space, the vector of king and the vector of queen will be very similar. They will be around each other. Let's say if we take another word like cricketer, then we are representing cricketer also with five words, but we are representing it with the number five. Okay, we are representing it with the number five, but this five dimensional vector will look very differently from both of these. It will go uh, like you can see here, this dimension will go like this for king, and similarly it come across closely for queen, but for cricketer it will go this opposite direction. Okay, so that's the beauty of embedding. Okay, if we go into a little more detail, then here every dimension reveals some aspect according to your data. Like it may be that this first dimension represents royalty. Obviously, if it is king, then this factor will be high. If it is queen, then this factor will be high. But if cricketer, this factor will be low, as I have shown you. The second aspect can be that it represents uh, athleticism. If it is a cricketer, then it will be a high, but if it is a queen and king, then this factor will be low. It can be third if it represents being human. Okay, if it is represent as a human, as these three separate what we can say, uh, persons or factors will be these factors will be low. It can be third if it is represent being as a human. Then since cricketer is also human, a king is also human, a queen is also human, so all three word will be high. So basically these dimensions have a meaning. we cannot actually understand it because the neural network does not tell us what that dimension is. But every dimension has a meaning, and the similarity of every dimension is seen. So on the whole two very similar words will be have very similar looking factors, and these similar words will be different looking vectors. This is the main idea. Now the embedded ones are strong and very useful, but there is a problem in embedding as well. So I just told you that what embeddings basically do is somehow that they are able to convert the meaning of a possible word into a vector. They have this capability, but sometimes this capability can also cause harm. How? I will explain you. So let's assume for a moment that we are training our own word embedding, and we have our own data. Okay, so these are all sentences, thousands and millions of sentences, and right now all these sentences are focused on a single word, that is apple. Okay, let's say we are creating our own embedding. So now all these sentences are focusing on a single word, that is apple. Okay, that is, I have kept it like this intentionally. I want to explain something to you. So we also created a neural network. Here is our training data. Here we are sending the sentences inside this neural network, and from here we are getting our vector. To keep things simple, we will take a two-dimensional vector. This means including every word of this training data, we will represent the word apple in two dimensions. And let us assume for a moment that these two dimensions will be there. The first dimension will be represent that taste. Okay, so assume that we have created our training data. This is our training data. These are the neural networks. So assume that first word we have represented as apple as the taste, and the second word apple as a technology, mobile phone. Okay. So the first dimension will be represented the test from the beginning, and the second dimension will be represent the technology. This means that we are relating each word according to two things. How uh, is its taste? How is it taste? And how much technology component is there in it? I know this is not logical for other things, but at least for Apple is logical. So the problem is that our word embedded model does not actually capture the meaning. Okay, it captures the average meaning. What does average meaning means? That on an average, with what meaning has that particular word been used in your data. Like I will explain this with an example. uh, Take example word. So suppose this first sentence get keep into our model. Okay, then what will happen to model? So what did this model understand? If you read an apple a day keeps the doctor away, it seems as if they are talking about apple as a food item. So obviously the taste component will increase. Okay, so it generates the components. Obviously the taste component will increase. Okay, the technology component will be zero. When the second sentence comes, apple is healthy, then what does it mean? Like when second this second then second sentence will come, then what does it means? That apple is a food item, right? So it must be related to taste. So we become a little more sure. What can we do about the taste component? We can increase this component a little more. Suppose we put zero point 0.7. Okay, then comes the third sentence, apple is better than orange. Okay, again it seems as they are talking about taste. So to become a little more sure, we pointed it out, the technology component is still not touched. The fourth sentence is Apple makes great phones. No, so this is a different context, right? And reading this sentence, it seems as if Apple technology is reading this sentence, we are getting that we are talking about Apple as a technology, right? So the weighted of this thing will increase a little here. Okay, so it will get increased here. Then in the same way, more sentences will come, where sometimes they'll this will come as a fruit, sometimes this will come as a company. So let us assume that if there are 10,000 sentences in our data, okay, then it comes in 9,000 sentences as a fruit, and in 1,000 sentences it comes as a phone company. So obviously the overall vector that will be formed will probably looking something like this. Right test will have a very high value because the amount of words are uh, 90%, right? A very high value. Technology will have a very low value, because if you talk about this entire data, then the average meaning of word apple in this entire data is more tilted towards taste in comparison to technology. If I can show it by drawing, if this is your taste dimension and this is your technology dimension, then there is a good chance after seeing this entire data your word vector of apple will look something like this. Okay, so I'm just trying to say how the word embedding will appear. It depends on your data set, okay? Because word embedding basically represents the average meaning of any particular word, not the meaning itself. But the average meaning in a vector, uh, I hope you understood. So what is the problem? The problem is that word embeddings are created once and are used again and again. This means that these are static words. This word embedding of apple is created now. I am going to use the same word embedding everywhere. Okay, so uh, no, this is a problem. I will explain it to you through an example. Suppose I am making a small NLP application whose job is to perform translation between English and Hindi. I have been given a sentence. Let's say the sentence is Apple launched a new phone while I was eating an orange. Example, Apple launched a new phone while I was eating an orange. Okay, so we have to convert this sentence into Hindi. What will you do first? If you convert all these words into their relative embeddings, then the problem has arisen. What is the embedding of Apple? Zero point 0.9. Okay, what is the embedding of Apple? Zero point 0.9 and 0.3, and this embedding is static, and it assumes that wherever apple is being used, it will be as a fruit. But clearly you can see that in this current sentence apple is actually used as an iphone company, okay, a technology company. So what should be ideal? Ideally you should have contextual embedding instead of static embedding. Contextual embedding means that these value change dynamically based on the context. Uh, meaning, what I mean is, if we talk about this sentence, as soon as we see in this sentence that the word launch has come, the word phone has come, then it should automatically increase the technology component and decrease the fruit and taste component. And it should be so smart that it does not get confused with this orange, because orange is being used in this sentence. Okay, so no one will feel that this apple is a fruit. But no, we need such smart context embeddings that it can adjust its embedding values according to the context in which a particular word is used in a sentence. And our word embedding cannot do this because it is static. it is trained only once. It is trained only once. It happens again and again. To solve this problem, self attention is introduced. Now the actual game is starting, so just focus from here. Self attention is such a mechanism which generates smart context embedding for you. From word embeddings, it will generate smart context embedding. Okay, what I means, consider self attention as a function where you send the entire sentence. Means when you send the embedding of each word, then you are sending the embedding of apple, you are sending the embedding of launch, you are sending the embedding of the phone, you are sending the embedding of orange, and here some calculations happen inside. Okay, so when we are sending the embedding of orange, so here some calculations will happen, which which gives you new embeddings here for apple, for launch, for orange, and for everyone. Basically for every input you get one output, one output embedding. But these output embeddings are actually smart contextual embeddings, and they understand in which context a particular word is being used. Basically for in every input you get one output embedding, but these output embeddings are actually smart contextual embeddings. Okay, and they understand in which context a particular word is being used, and then you use this further in architecture like transformers. So I hope after a very long discussion, I explained to you what is self-attention. I really hope I was able to explain to you in a simple one-line summary that self-attention is a mechanism that can take static embeddings as input and can generate good context embeddings which are be used for any kind of NLP application. So now going forward in this video, our only goal is to understand what calculation is going inside here. Okay, what has been what has been understood, we are going to move on, like onto how, the how part, like which so far we have talked about the what part, and in our further videos we are going to talk about the how the work is going on, how the calculations behind the scene is going on. Okay, so I know it was a very short and simple video, and its goal was also very small. I just want to explain to you what is self-attention. Now, if you are excited, then in the next video we will discuss how self-attention works, and there are and there we will understand some concepts like what are query key and value factors, and how to use them self-attention mechanism to create context embedding. So the next 2 3 videos are very interesting. I am super excited, and also I hope you are too. See you in the next video.